If the cosmic microwave background is the oldest photograph of the universe, then scientists have spent decades trying to improve its resolution. The first glimpse proved that the ancient light existed, but researchers wanted to know something even more remarkable. Could this afterglow reveal how every galaxy, every cluster, and every enormous cosmic structure came to exist? To answer that question, humanity built some of the most sophisticated space observatories ever created. The first major breakthrough came with NASA's Cosmic Background Explorer, better known as COBE, launched in 1989. COBE's mission was simple in concept, but revolutionary in practice. Measure the oldest light in the universe with unprecedented accuracy. What it discovered changed cosmology forever. COBE confirmed that the cosmic microwave background was almost perfectly uniform, but almost turned out to be the most important word in modern astronomy. Hidden within that ancient glow were tiny temperature differences, only about 1 part in 100,000. Imagine standing beside Mount Everest and noticing a pebble only a few centimeters high. That's how unbelievably small these differences were compared to the overall temperature of the universe. Yet those tiny variations became the seeds from which everything else grew. When COBE announced its results, scientists celebrated because they had finally found the fingerprints of the early universe. These faint ripples represented the first evidence of the density fluctuations predicted by the Big Bang theory. But COBE had only begun the story. A few years later, NASA launched another mission called the Wilkinson Microwave Anisotropy Probe, or WMAP. If COBE had given humanity the universe's baby picture, WMAP provided a high-definition portrait. For 9 years, WMAP carefully measured the temperature of the cosmic microwave background across the entire sky. Every tiny variation became clearer than ever before. The mission revealed that the universe is approximately 13.8 billion years old. It also showed that ordinary matter, the atoms making up stars, planets, and people, accounts for only a small fraction of everything that exists. The rest is composed of two mysterious ingredients: dark matter and dark energy. Think about that for a moment. Everything you've ever touched, every mountain, every ocean, every galaxy visible through a telescope, represents less than 5% of the entire universe. The remaining 95% is something we still don't fully understand. And scientists discovered this by studying light that has been traveling across space since the universe was only 380,000 years old. Then came another leap forward. The European Space Agency's Planck satellite produced the most detailed map of the cosmic microwave background ever created. Its observations revealed temperature differences so tiny that they resemble the delicate brushstrokes of a masterpiece. Each warm and cool spot on that map corresponds to slight differences in matter density during the universe's infancy. Those tiny differences became stronger under gravity. Regions containing just a little more matter attracted even more material over millions of years. Clouds of hydrogen and helium slowly collapsed. The first stars ignited. Galaxies assembled. Galaxy clusters emerged. Eventually, the enormous cosmic web stretched across billions of light years. Today, when astronomers map the distribution of galaxies throughout the observable universe, they see patterns remarkably similar to those first imprinted within the cosmic microwave background. It's almost as if the universe followed its own architectural blueprint with astonishing precision. Imagine planting millions of tiny seeds across an empty field. At first, the field looks almost identical everywhere. But over time, each seed grows into a tree. Eventually, forests emerge. The cosmic microwave background contained those original seeds. Gravity simply allowed them to grow. This is why cosmologists often describe the CMB as the universe's blueprint. Without those microscopic fluctuations, gravity would have had nothing to amplify. Matter would remain evenly spread across space. No stars would ignite. No galaxies would exist. No planets would form. And life, as far as we understand it, might never have appeared. Perhaps the most astonishing realization is this. Every galaxy you've ever seen in breathtaking telescope images, every star visible in the night sky, every black hole, every nebula, every planet, Even the Milky Way itself can trace its origins back to tiny temperature fluctuations frozen into light nearly 13.8 billion years ago. In other words, the structure of today's universe was quietly written into the oldest light long before the first star ever shined. The cosmic microwave background is not merely ancient light. It is the universe remembering its own birth. And every time scientists create a more detailed map of that ancient afterglow, they uncover another chapter in the story of how a nearly uniform sea of particles evolved into the breathtaking cosmos we call home. In Part 3, we'll explore how the cosmic microwave background continues to test the limits of modern physics, reveal clues about cosmic inflation, expose one of astronomy's biggest mysteries, the Hubble tension, and help scientists search for answers about what may have existed before the Big Bang itself.